Welcome to our new video series. We're testing out newer approaches to explain AI, and we need your feedback. Is it too easy? Too complex? Let us know in the comments. We love hearing your ideas for future videos as well. Please share, like, and subscribe if you find this useful. Our mission today is focused on engineering agentic AI workflows. This represents a fundamental shift in how we think about automation. We are moving beyond the confines of rigid, predefined steps and stepping into the era of intelligent, adaptive systems. For years, automation meant building siloed, solo operations, where a single script performed a single task. But just as the most complex intelligence missions require a diverse team, the future of AI automation lies in coordinated effort. We are transforming those solo operatives into highly specialized, coordinated crews. Critically, we are accomplishing this using no-code platforms. This democratization of advanced AI means that complex, multi-step workflows that previously required months of bespoke development are now accessible to every enterprise builder. This presentation serves as your briefing on the architecture, protocols, and coordination patterns necessary to deploy these intelligent systems successfully in production environments. Pay close attention, as understanding this framework is key to unlocking the true potential of intelligent automation in your organization. To understand agentic workflows, we must first establish the difference between traditional automation and what we call an intelligent operative. We title this slide the briefing, a new class of operative. Traditional automation, which we call the script, is essentially a choreographed dance. Every step is rigid, predefined, and deterministic. It is reliable only because it is completely inflexible. If an unexpected input occurs, the script breaks. It cannot adapt. Now contrast this with an experienced intelligence analyst. They don't just follow a script, they possess a cognitive rhythm. This rhythm is the core of agentic AI. Think, act, observe, iterate. Agentic AI digitizes this natural rhythm, allowing the system to operate at machine speed and scale. This is the conversation. Instead of following a rigid path, the agent and its tools interact dynamically. The workflow path evolves based on feedback and dialogue. The destination emerges through continuous adaptation. The system constantly monitors its output and adjusts its strategy based on what it learns during runtime. This ability to reason, self-correct, and adapt is what defines the new class of operative and gives agentic workflows the power to tackle complex, unstructured problems that were previously out of reach for traditional automation. When deploying these systems, we need to know exactly how much autonomy we are granting the AI. Not all agentic systems are equally autonomous. We classify them into 3 levels of decision-making to define our mission parameters, which we refer to as the threat assessment. Know your automation levels. Level 1 is output decisions, personified by the informant. This is typical of most chatbots. The AI decides what to say, but the reasoning process is internal to the model, and the system architecture remains fundamentally linear. There is no external action or looping. Level 2 is task-level decisions, represented by the field agent. This is our primary focus for enterprise applications. Here, the AI decides which tool to use or which specific task to execute from a predefined set of options. The agent gains autonomy over its execution flow, allowing it to adapt its path in real time, but within a strictly controlled environment. It is using tools that we, the engineers, have provided. Finally, Level 3 is process decisions, known as the Ghost Protocol. This is the frontier, where systems like Baby AGI reside. The AI decides how to build its own process or even create new tools. While exciting conceptually, this level poses significant safety and reliability risks, making Level 2 the optimal target for current, stable enterprise missions that require real-world action and reliability. The engine that drives this new class of operative is called the core protocol, the RAACT reasoning loop. RAACT, which stands for Reason plus Act, is the most influential pattern in agentic systems. Its power lies in its ability to ground the agent by interleaving its reasoning or its inner monologue with concrete actions taken in the real world. Let us walk through this critical 4-step cycle. The loop begins with Step 1, thought. This is where the agent formulates a strategic plan based on the current situation and memory. For instance, the thought might be, I need to check the target's financial profile. This thought determines the next step. That leads us to step 2, action. Based on its thought, the agent invokes a specific tool, such as calling a credit check API or a database query. This action executes a command in the outside world. The third step is observation. The tool returns new information, or intel, such as credit report data or a file status. This new intel is crucial, and it is immediately added to the agent's working memory, providing context for future decisions. Finally, we reach step 4, loop or terminate. The agent analyzes all the new intel. If the original mission is complete, it provides a final answer and terminates. If not, if the information is incomplete or a new direction is required, it loops back to the thought phase, refining its strategy based on the observation. This constant cycling between thought and action is what allows the agent to navigate complex, multi-step tasks dynamically. While the React loop is powerful, a single agent can still produce outputs that are plausible but ultimately flawed or incomplete. To mitigate this risk and ensure mission quality, we employ an advanced technique, the two-agent rule. This rule uses a reflection and refinement pattern achieved by pairing a generator agent with an evaluator agent. Agent 1 is the generator. Its job is straightforward: draft the initial plan, compose the analysis, or formulate the message. It completes the core task. However, this output is not immediately released. Instead, it is routed to Agent 2, the evaluator. The evaluator acts as a critic or quality control. It rigorously reviews the generator's output against a predefined specific rubric. This rubric checks for completeness, logical soundness, adherence to mission parameters, and crucially, whether the output contains factual inaccuracies or hallucinations. If the output passes all these checks, it is approved for output. If, however, the evaluator finds deficiencies, it provides structured feedback, triggering a revision required flag. The output then loops back to the generator, which uses the feedback to revise its work. This robust loop continues, iterating the output, until it meets the established quality thresholds or a maximum iteration limit is reached, ensuring a significantly higher standard of reliability for high-stakes outputs. An agent's effectiveness is entirely dependent on its ability to remember and learn, making memory management a critical engineering discipline. We implement two distinct types of memory systems, which we call mission intel, short-term versus long-term memory. These two systems serve fundamentally different functions in the agent's cognitive stack. First, we have short-term memory, symbolized by the radio. This memory is ephemeral and holds the context only for the current session or task. Its function is to hold the current conversation history and intermediate results of the ongoing React loop. In platforms like n8n, this lives primarily in the active workflow context, often referred to as a window buffer memory. The query method for SDM is a full context replay, meaning the entire recent history is passed to the language model for immediate reference. In contrast, we have long-term memory, or the dossier. This memory is persistent, spanning across all sessions and historical activities. Its function is to store persistent organizational knowledge, historical patterns, learned strategies, and proprietary information. The storage for LTM lives externally, typically in dedicated external databases, vector stores, or knowledge graphs. The way we query this crucial information is through retrieval augmented generation, or RAG, or via direct lookup. By separating these concerns, we ensure the agent has fast access to immediate context while being able to draw deeply on the organization's collective intelligence without overwhelming its context window. While single agents are adept at solving complex problems, the true breakthrough comes from assembling the crew through multi-agent orchestration. For high-stakes, highly complex missions, a team of specialists will invariably outperform a single generalist agent. A specialized agent, focused intensely on a specific domain, equipped with access to tailored tools and restricted knowledge relevant only to its domain, delivers far higher quality and more accurate results than any single monolithic model. The challenge then becomes how to coordinate this team effectively. We address this by building multi-agent systems using coordination patterns. These patterns are formal, repeatable ways of orchestrating how individual agents interact, how they hand off work to one another, and how they ultimately collaborate effectively toward a common goal. This architectural design ensures predictability and scalability in complex workflows. Over the next 3 slides, we will introduce and detail the 3 core coordination patterns that you can implement for your agentic crew, moving from simple sequential flows to dynamic, hierarchical systems. The first core coordination pattern is crew formation 1, the assembly line, which we formally call sequential refinement. This pattern is perhaps the simplest and most intuitive to deploy. Agents work strictly in a linear sequence, where each agent processes the task in successive stages and is responsible for refining the work received from the agent immediately before it. This pattern is ideal for tasks that naturally have clear, ordered phases and where quality measurably improves through focused, iterative refinement at each handoff point. Let us look at a typical content creation example. The process begins with the researcher, whose function is to gather all the necessary raw intel and compile comprehensive research notes. This output is then passed to the next agent, the architect. The architect takes the raw research and imposes structure, creating a formal, logically sound outline. That outline then moves to the writer, who drafts the full content based strictly on the prepared outline, ensuring structural integrity. Finally, the draft moves to the editor, whose job is highly focused, polishing the draft for clarity, tone, and strict brand alignment. The assembly line ensures high-quality output by segmenting complexity and forcing iterative improvement at every stage of the workflow. Our second core coordination pattern is crew formation 2, the pincer movement, formerly known as concurrent specialization. This pattern is designed for speed and comprehensive coverage when dealing with multifaceted problems. Instead of linear handoffs, multiple specialist agents work on distinctly different aspects of the same problem simultaneously, in parallel. Their individual, specialized findings are then brought together and merged by a single, central synthesizer agent to form one comprehensive conclusion. Consider the example of developing a customer retention strategy, starting with initial data. This data is fed concurrently to 3 specialized agents. The financial agent analyzes all the customer's purchase history. At the same time, the engagement agent analyzes their interaction history across all channels. Meanwhile, the risk agent analyzes specific churn indicators and proprietary risk metrics. All 3 agents work independently, diving deep into their domain. Their separate insights are then routed to the Merge Insights node, which ultimately feeds the data to the critical final component, the retention agent, which serves as the synthesizer. This agent's core mission is to merge all the disparate financial, engagement, and risk findings and propose a single, targeted, high-impact retention strategy. This parallel approach ensures maximum analytical depth and workflow speed. The third and perhaps most sophisticated coordination pattern is crew formation 3, the mission commander, which we define as hierarchical routing. In this structure, a primary orchestrator agent acts as the commander and central intelligence hub. Its crucial role is to assess the incoming task, whether it is an unstructured customer request or a complex internal mandate, determine the precise specialist required to handle the task, and delegate the task accordingly to the correct subordinate agent. This pattern is exceptionally effective for triage and complex customer service operations. The orchestrator agent, the commander, receives an incoming customer ticket. Its first step is to analyze the text and determine the user's intent with high accuracy. Based on this intent, it routes the task to the most suitable specialist. If the intent involves financial matters, the task is delegated to the billing agent, which is equipped to handle billing issues. If the request is about technical problems or features, it goes to the product agent. And if the inquiry concerns delivery logistics, the order status agent takes over. This hierarchical routing prevents specialized agents from wasting cycles on irrelevant tasks, dramatically improving efficiency and ensuring that every issue is handled immediately by the agent with the highest domain knowledge and the correct tooling. To move these conceptual patterns into production, we need a physical blueprint. This is the blueprint, your mission toolkit in n8n, which maps the theoretical agent concepts to practical workflow nodes. These agentic workflows are engineered and built using a specific set of interconnected nodes, each serving a distinct, specialized role in the mission plan. The core operative, the reasoning engine of the entire mission, is the AI agent node, which we call the mastermind. This is the component that executes the React loop, driving the system's intelligence. For the mastermind to take action in the real world, it needs specialized equipment. These are the tool nodes, the gadgets, which provide access to APIs, databases, or custom functions. These are the means by which the agent interacts with external systems. To manage context and organizational knowledge, we utilize memory nodes, known as the Intel database. This component holds both the short-term conversation context and the long-term knowledge, often through RAG. Finally, in multi-agent systems, the mastermind needs a way to call in support. This is achieved through the AI agent tool node, or the secure channel. This node acts as a radio, allowing one specialized agent to call upon and delegate tasks to another specialized agent for support or specialized analysis, completing the structure necessary for robust, collaborative workflows. Let us examine a practical example of the sequential refinement pattern in a high-value, high-stakes domain: mission simulation, operation loan approval. The objective here is massive: to automate the initial assessment of a loan application, slashing a typical 3 to 5 day manual process down to under an hour, all while maintaining strict consistency and ensuring complex or problematic cases are correctly escalated. This mission utilizes 5 specialized steps. It begins with the document agent, the quartermaster, which extracts and validates structured data from complex, unstructured application documents. Next, the financial agent, the analyst, analyzes creditworthiness and risk. It uses dedicated tools to retrieve credit scores, calculate crucial debt-to-income ratios, and run proprietary risk scoring models. The third agent is the compliance agent, the lawyer, whose function is to ensure the application meets all stringent regulatory requirements, such as KYC and AML, alongside internal bank policies. Once the data is refined and checked, it moves to the decision agent, the commander. This agent's sole purpose is synthesis. It draws intel from the first 3 agents and uses all findings to recommend a final, objective decision. Finally, we integrate the human in the loop, or mission control. The agent's recommendation, coupled with its full, transparent reasoning, is escalated to a human loan officer for the ultimate, non-automated final sign-off. This entire workflow maintains speed and consistency while guaranteeing necessary human oversight for crucial decisions. Building reliable agentic systems requires us to anticipate where failure is most likely to occur. This leads us to our discussion on evasion and countermeasures, avoiding mission failure. A successful mission hinges on proactively bypassing or neutralizing common operational pitfalls. One major risk is context window exhaustion, where the agent's working memory becomes saturated, leading to drift or poor performance. The tactic here is summarization. Periodically create structured, field reports summarizing the progress made so far to compress the context, freeing up the working memory for new information. Another threat is tool unreliability. External tools or APIs may fail or return bad data. Our countermeasure is redundancy. Build in robust retry logic and always provide backup tools or data sources, such as having a secondary database ready if the primary fails. A major architectural threat is infinite loops. Agents can sometimes get stuck in a cyclical thought pattern. We neutralize this with mission timers. Set strict maximum iteration limits on the React loop. If this limit is reached, the agent must escalate the case to a human or terminate gracefully. Finally, we must guard against scope creep, where the agent drifts away from its original mission objective. The tactic here is strict rules of engagement. Define precise goals and provide a strictly limited toolset. If the agent only has tools necessary for the task, it cannot deviate into unintended operations. These countermeasures are essential for moving from experimental agents to reliable production systems. Before deploying resources, we must critically evaluate whether an agentic approach is truly the optimal choice. This is our mission debrief: when to deploy your agentic crew. The key to operational success is knowing when to deploy an adaptive agentic crew versus using a traditional, rigid automated drone. It is a strategic choice based entirely on the nature of the task at hand. You should deploy an agentic crew when tasks are complex, deeply knowledge-based, and multi-step, such as detailed research, financial analysis, or creative content generation. Agentic crews are also essential when adaptability is highly valuable and exceptions are common, for example, in complex customer support scenarios. And critically, they are needed when decisions depend on synthesizing diverse, often conflicting, information sources. Conversely, use traditional automation when processes are rigid, high volume, and deterministic, such as standard data ETL or structured report generation. Traditional automation is superior when low latency is critical and errors would be catastrophic, such as in payment processing or real-time transactional systems. Lastly, use traditional methods when predictability, raw performance, and low operational cost are the primary drivers. The key insight derived from this comparison is that the optimal strategy is nearly always a hybrid approach. This means strategically leveraging agentic intelligence for high judgment, complex tasks, and relying on traditional automation for high volume, low judgment, foundational steps. We conclude today's briefing with the clear message that the future is agentic. We have moved into a new era of capability, establishing a new category of software we call intelligent automation. This system is fundamentally distinct from rigid robotic process automation and simple, conversational chatbots. This is automation that reasons, adapts, specializes, and collaborates dynamically. A crucial element of this transformation is democratization. No-code platforms like n8n have effectively democratized access to these advanced capabilities. By providing nodes for React, memory, and orchestration, they are empowering everyday engineers to design sophisticated, intelligent systems that previously required months of highly bespoke AI development and specialized expertise. This shift in access is rapidly accelerating the adoption curve. Finally, we must understand the true mission. The ultimate goal of agentic AI is not to build systems that attempt to think like humans, which is often unreliable and fraught with ethical challenges. Rather, the goal is to build powerful systems that reason alongside humans. By creating these intelligent crews that handle the iterative, complex, and data-heavy analysis, we are effectively amplifying our own human judgment and freeing us, the human operators, to focus our efforts entirely on high-level strategy, creative problem-solving, and making the final critical decisions.